Okay, so I will get started. The plan today is to just do a quick review of what you've learned this week and then do some practice problems. And then if anyone has questions at the end, feel free to ask and I can get those answered for you. So I'm just sharing my screen here. And just to make sure you all can hear me, right? I hope so. Um, I'm just going to assume you guys can hear me. Yep, okay. All right, so getting started. This week, you really learned, the main things you learned are the node voltage and mesh current methods of solving circuits. So as a quick refresher, I'll start with node voltage. Node voltage is a method of creating equations that you can then solve to find values in a circuit. So the basic circuit you might have might look something like this. I don't know, maybe you have some kind of dependent source here and voltage source here and some other resistor up here. And so like there's a lot going on in this circuit. And what node voltage allows you to do is by selecting points in your circuit and defining them as, I don't know, V1, V2. And here this would just be whatever this voltage source is. It allows you to create equations and use those to solve your circuit. So I will give everything a name here. And this can be Ti, and this can be R1, 2, and 3. So just as a quick refresher, what you want to do with node voltage is, so for each of your nodes that you select to make equations about, so let's start with V1, you'd write an equation based on Kirchhoff's current law. So Kirchhoff's current law says that the total current through any node is zero, also known as the current going in equals the current going out. So what that means in practice, however, is that for a given node, you kind of guess which direction the current is going in. And then based on that, write out your equations. So here, I'll write in blue here. So for V1, we know there is a current going down. We can assume, or we're guessing there's a current going to the right. And I'll just say, for the sake of argument, there might be a current going to the right there. What's key to note here is that it doesn't actually matter what direction you're guessing because the math will turn out the same no matter what. And so I'll just do it just for this node because I'll get back to it when we're doing practice problems. But V1 would be something like V1. So I'll start with the current from the left. So it would be actually, and key to note, current in is negative, out is positive. So for V1, we'd have I, or actually I'll write I on top. So we'd have minus, because it's going in, Vs minus V1 over that R1. And this here is the I that I've labeled there. And then plus, because the other two are going out, they're both going to be plus 2I plus V1 minus V2 over R3. And that will equal 0 because the sum of those currents is going to be 0. So that's, again, just an example. I'll get to actual problems with it later. And then mesh current, that's mech current. Mesh current, whoever, can you guys be sure to mute yourself? Mesh current is similar, so I'll just actually copy, actually, no, I don't want to copy that one. Oh, yeah, I'll copy it and then change it slightly. So mesh current, instead of using the nodes, we are going to use what we call meshes. I'm going to change this a bit to make this a voltage source because that will make the circuit make a bit more sense. Generally, if you're working on a circuit and it has a bunch of currents, then you want to do node voltage because node voltage, each of these terms has the unit of amps. So if you're dealing with currents, node voltage is often better. if you're dealing with a lot of voltage sources, then mesh current can be better. It's not that tried and true. It's not like that cut and dry, because as you'll probably see in class or you've seen some examples, sometimes current sources can make mesh current very easy. But for now, especially with like dependent sources, it's pretty good to say that as a rule for now. So here for mesh current, right, we define some imaginary currents in the different like circles of our circuit. So usually it is custom to make them go counterclockwise. It just makes your math nice and consistent. Let me actually make these a different color just for emphasis. So here, this can be I1. This can be I2. And I didn't really leave enough room for myself there, but that can be I3. And what you do is, so let me write, this is KCL. Now we're going to, so it's kind of counterintuitive because for node voltage, you're using the current law, whereas for mesh current, you're using the voltage law. So it's opposite, but that's the way it works. So let's say for I1, right, we write a KVL equation around that I1 loop. So what that's going to look like here is thinking back to your, what's it called? Thinking back to the sign, what's it called? The rule that says when voltages are positive or negative. I'm blanking on the name right now, but you guys know what I'm talking about. Here, this voltage source, because it is in the same direction of the current, it's going to be a negative Vs, because we want the voltage drop to agree with the current. Here, the voltage is going up, so it's negative. And then plus, we have that R1, so that's going to be some resistance. And then here is where it gets, this is where you actually create the relations between the equations of mesh current. It's going to be I1 minus I3, because in this resistor, right, it has this total current I going to the right, but that total current I is composed of an I1 going this way and an I3 going that way. So when you add those two together, you'll get I1 minus I3. And similarly, well, actually, just to keep going with this loop, I'll do 2 loops in this time. And then the third one is going to be plus 2I. And this is a voltage this time, because that 2I, it has a voltage drop in the same direction as that current I1. I'll do the I3 loop next, because that one will kind of drive home the point I'm trying to make. The I3 loop is going to be, so the I3 loop, I'll start with the R1. So it's going to be R1 times, now, since we're looking from the perspective of I3, now I3 is the positive current and I1 is the negative current. So we're going to have R1, I3 minus I1, and then plus R2. And still I3, and then there's actually no other current for this one because it's all on its own. So you can really just write that as R2 times I3. And that's because, as you can see, R2, it's only influenced by that current I3. And then R3, just like the other one, is going to be I3 minus I2 equals 0. And you could do this for the next 3, but I'm going to do some actual practice problems in a bit instead of this circuit that I just made up on the spot. And yeah. And then the other 2 things that I believe you learned this week are supernode and supermesh. So supernode, let me, again, kind of just alter this circuit, or this one I started with. So if you had a circuit like this, but let's say we swap the position of these 2 components because we want to make our lives just that much harder. And this is, let's say, 3 volts. I'll just say 3 volts right now so that something has a concrete number. And this can be R1. So then what we do is, the issue with node voltage here is that when you try to write the node equations for this node and this node, right, you have some unknown current here that makes your equations really hard to deal with. So what you do instead is you utilize the fact that this voltage source tells you directly that, oh, this should be, let me rename these real quick. So now this is V1, V2, and V3. So what that voltage source there does is it tells you directly that the difference between the voltage at V1 and the voltage at V2 is 3 volts, because there's a voltage source there between them, which you can think of, the other symbol for a voltage source, if any of you have learned this, is something like this, where what it tells you is that on one side of the gap, there is some voltage difference than the other side of the gap. So this kind of makes more sense in this scenario. It's telling you that V1 is 3 volts lower than V2. So that's really the core of the supernode. So to start the supernode, you have your supernode equation, which in this case can be V1 plus 3 volts equals V2. And that kind of makes everything a whole lot easier. So then what you do after this is you write your normal node voltage equation, but as if these two nodes together were just one node. So both of those nodes combined, all of their connections create the supernode, like bigger equation. However, you still use the same kind of terms as you learned in node voltage. So you're still only using one V1 or V2 at a time. So just as an example here, starting with that R1 path, we have V1, oh, I'm still in dashed line mode. So supernode, so at the supernode, we'd have V1 minus 0 over R1. I often like to just assume that every current is going out because it makes the math a lot easier. That math always works out the same no matter what direction you choose. So if you're dealing with a resistor, it's kind of good practice to just always assume the current is going out of the node and then all your numbers are positive and you don't have to mess with anything. However, if you do have a current source, then you do actually have to pay attention to the sign. But for now, it's really easy, right? So V1 minus 0 over R1, that's that first path. And then V1 minus V3 over R2. And that covers all of the currents going in and out of V1. But then we're still talking about the same node, the same supernode. So we'd have V2 minus V3, this is the one going to the right, over R3, and then plus just that 2I current source. And that would be your supernode equation. And then you'd write the equation for V3 as well. And then once you have that, you should have enough information to solve for the rest of the circuit. So I believe that's all the new content that you've really covered this week. And now I will just kind of get into some practice problems. So to start, I'm going to actually go over a question. Actually, no, I'll do this one's good. Yeah, I'll do this one. Okay, I was gonna do one from the homework, but you guys can look at the answer key from the homework for that. I think this question is good, so I'll start out drawing it. Give me a second here. In this question, we're going to be using node voltage to solve it. Or actually, yeah, we're just gonna do the node voltage equations because often on quizzes, that's all they actually ask for. If you have a big series of big system of equations, usually we will just ask you to write down the equations and not actually solve them because frankly, you do not have the time, nor is it worth the effort of you or the grading TAs to go through all of that algebra. So okay. So this is our question, and it is just the stated purpose here is to write the node voltage equations as if you're about to solve it. So to begin, we need to define a 0 volts and define which nodes we're looking at. So generally, for any circuit you're going to get in this class, it's almost definitely going to be drawn where you just put the 0 volts at the bottom. In practice, you want to put it where the most nodes connect or wherever it'll make your life easiest. You could put it in other places and your math will turn out exactly the same. However, it's probably just going to be best to put it at the bottom of the picture. So that's what I'm doing here. This is 0 volts. You can also see this drawn as like a little arrow sometimes. They're all basically the same thing. They have slightly different meanings if you get more into electrical engineering, but for now, they're all just 0 volts. And then we define all the nodes where things meet, where all different components meet, as in 3 or more components. So this can be V1, this can be V2, and this can be V3. And that tells me that that's going to be 3 equations there. And then we're going to have one more equation for this dependent voltage source, or for defining what I is. So let's start. So the V1 equation, straightforward. It's going to be V1. As I said earlier, I am going to be assuming that all currents are going out of every node, because that makes everything way, way easier. And if someone wants at the end, I could give like a proof of why it doesn't matter what direction you pick. Basically, when you assume it's going the other way, you put a negative sign on the front, and then when you factor in that negative sign, it turns positive anyway, so it really doesn't matter. Anyway, I highly recommend just assume every current is going out unless you are explicitly told by a current source that it's going in. So here, right, we're going to have, starting with the one going down, we're going to have V1 minus 0 over 5 ohms plus, and then I'll do the one going up, V1 minus V3 over 25 ohms. And then this third one is kind of tricky because we have a voltage source. However, what you have to remember here is that we're looking at currents. So the current for this path is largely going to be determined, or it's entirely going to be determined by what the voltage is on either side of this resistor. Because the voltage sources don't directly impact the current, they only affect the current in how they affect the resistors. So what that means in the end is we want to look at what the voltage is on either side of this resistor. So on the right side, of course, it's just going to be V2. And then on the left side, right, we have V1 here, and then it goes up this dependent voltage source. So what we can write this as is V1 plus 2.5I. So what we have in the end is the current through that resistor can be written as, I'll put it in parentheses just to make it a bit more clear, V1 plus 2.5I, the difference between the two, and then over 5 ohms. And that equals 0, and that's your first equation. For V2, it's largely the same thing. I'm just going to kind of plug away here and get going. So for the next one, it's going to be the negative version of the other one. The negative version of the one we just did, basically. Hopefully that is pretty clear why. And then for the one going down, I'll say V2 minus 0 over 10 ohms. And then for the one going to the right, it's going to be V2 minus V3 over 5 ohms. 0. For V3, we have a similar situation for the path going down as we did before. So again, even though there's a voltage source here that's giving a positive 10 volts going upwards, you can still assume that all currents are going out, and the math will still work out just the same. It makes all your numbers positive. It's very good. So to start with the one going down, right, we have V3 minus, and then just in the same way I did with that dependent source earlier, you can think of this as 0 plus 10 volts over that 10 ohms, because if we have 0 volts down here and we go up to here, then we're going to have 10 volts here, which means through this resistor, we have V3 minus 10 volts as the difference. And just putting in parentheses like that makes it really clear. And then continuing on, V3 minus V2 over 5 ohms. That's the path going to the left. That doesn't really look like a 5. I'll redraw it. And then finally, the path going up, we have V3 minus V1 over 25 ohms. And then you might think we're done here, but we have one small minor thing to do left. Right now we have 3 equations and actually 4 unknowns because of this here. So we need to write our dependent source equation, which is simply just defining what I is. And as we can pretty clearly see from the circuit, I is just going to be equal to V2 minus 0 volts over 10 ohms. And with that, that's all that they would ask you to do on a quiz. If you generally, on a quiz, if there are 3 equations, they're not going to ask you to solve it unless there's like some really easy way to do it, because they can't expect you to simplify 3 equations in that short amount of time. Maybe I'll be wrong and they will do that because they're mean, but for this will probably be pretty similar to what you'll get on the quiz. So moving on, I'll do a mesh current example. So here is the circuit. This one's a little bit simpler.
Will mesh current be on the quiz?
Probably. I don't exactly. Did he teach it mesh current and then super mesh, or did he teach it what order did he teach it in? Because I know you've learned node voltage, super node, mesh current, and like super mesh. Maybe have you learned?
Like super mesh wasn't on the homework, so
Okay.
I don't know if that meant it wasn't on the
Was
quiz.
mesh current on the homework?
No.
Oh, okay. Then it might just be. But you learned mesh current in class, right?
On Wednesday.
On Wednesday? Okay. Just looking at past quizzes, oftentimes this quiz is like one mesh current and one node voltage question. So I'll do this one just to be safe. But if he's structuring it how he's been doing it in class, or if he's keeping the quizzes up with like what you've learned in class, then there's a chance mesh current wouldn't be on it. But I'm still going to do this example. It can't hurt. Okay. And then I'll do a node voltage one at the end. But mesh current is pretty similar to node voltage in that you are using these things you create, or you don't create, but these things you name to make 3 equations that relate different quantities together, and then you use those equations to solve for the values you want. On the homeworks, of course, once you get your equations, you can just plug them into an equation solver, and it works just as well. Always good to practice doing algebra, as you do not have access to an equation solver during an exam. 2 ohms, 2 ohms, 6 ohms. This is so the prompt for this question is write all equations necessary to find mesh current. So as with any mesh current problem, you start by defining what currents you're looking at. So here, I1, I2, and I3. It doesn't really matter what order you name them in. It's all going to be the same thing in the end. So then just getting started with the equations. So for the I1, again, we're doing a KVL loop. So that resistor on the left, we have, for resistors, it's always going to be positive because a resistor cannot like have a negative voltage. That's just, it just can't. Just that's the nature of how they work. But so yeah, you're going to have 2 ohms. I'm not going to write the ohms because that's makes it look ugly. 2 I1, and then we have plus 3, And then this is going to be I1 minus I3. Again, that's because we have our I1 going to the right and the I3 going to the left. The total real current the total actual current going through this, you don't know which direction it's going, but it's going to be, depending on what direction you're like looking in quotes. Right now we're looking from the perspective of I1, which is going clockwise through this. So it's going from left to right through this. So we're saying that the positive current is I1 and the negative current is I3. When we do the I3 loop, it would be the other way around. So, as we said, it's I1 minus I3. Very similarly, for the 2 ohm in the middle, it's going to be 2 times I1 minus I2. And then that 48 volt source is actually going to be positive here because it has a voltage drop in the direction. Oh, passive sign convention. That's the word I was looking for earlier. It has a voltage drop in the direction of the current. And we always want a voltage drop in the direction of the current in order for it to be positive. So here we have a 45 volts. And that equals 0. So that's going to be your first equation. I2 is going to be very similar. Doing the same thing, just making 3 equations here. However, now, since the current is going, for I1 in that middle path, it was going from top to bottom. For I2, from that I2's perspective, is going from bottom to top. So now it's going to be a negative 48. And then that 2 ohm resistor is now going to be I2 minus I1. And that 6 ohm is going to be 6 I2 minus I3. And that's all you'd have there. So then I3 might look a bit tricky at first, but actually it's easier than the other ones. So I3, you might look at that 4 amp source and say, I don't know the voltage across that 4 amp source. And you'd be correct. You don't know the voltage across that 4 amp source. However, if you look at this 4 amp source, there's nothing else connected to it. And what we know is that there's a current of I3 going in that direction through the 4 amp source. But since the 4 amp source literally defines the current through that path, what we can say because of that is that just I3 equals negative 4 amps. Because I3 is going clockwise, however, the real current as defined by this current source is going to the left. And so that's 3 equations there. That's enough to basically solve for all values in the circuit. And then for Ix, because this is asking you to find all necessary equations to find Ix would actually be I2 minus I3, because just like I talked about with that 3 ohm resistor, we have this current component I2, and we have that other current component I3. And since the Ix we're talking about is going to the right, then we're talking about looking from the perspective of I2. So I2 is positive, I3 is negative, and that would be your equations. Okay, and then I might have had one more question I could do. Oh yeah, okay. I'll have one that might take a little bit, but this one will actually do the math through a pretty simple node voltage problem. And then that will be it. Unless there's other stuff you guys want me to cover. You have me for an hour, but if there's not more, then I will call it early. So we have our node. So this is our circuit, and the prompt is to find the power associated with the dependent voltage source. So And for this question, we're going to use node voltage. So to start, we want to define our ground or our 0 volts, whatever you want to call it. Like I said earlier, it's basic. Oh, this is 9 volts. It's basically always going to be the bottom. Here, you have a bunch of components connected on the bottom. It works out. And it just makes everything make more sense. And then the only real node we have besides that 0 volts is up here. Again, I think the terminology was like a unimportant node. It was some word like that. I'll call that V1. Actually, I'll call it V1. Let's start out by, since we only have one node, we're only going to really need to write one equation here. So V1, just like we did before, we got the current to the left. I'm going to, again, assume all currents are going out of the node to make my life easier. V1 minus 9, because right here is 9 volts, because it's 0 down here. And then we go up the 9-volt source to 9 volts. So across that resistor, we're getting V1 minus 9 over 20, about 20 ohms. And then we have V1 minus VA over 2 from the dependent source over 10. And then we have V1 minus 0 over 40. And then we could simplify this a bit. Let's say multiply everything by 40. You get 2V1 minus 18 plus 4V2 minus 2VA plus V1 equals 0. Wait, V2, I don't know why I wrote V2 there, my bad. Okay, combine like terms. 7 V1 minus 2VA equals 18. Moving that 18 to the other side. And then VA, we can write an equation for that pretty easy. VA is going to be actually one of the terms we already had. So this is VA. Look at that. This is such a good app. V1 minus 9 over 20. So then we can plug that in. So 7V1 minus 2 times V1 minus 9 over 20 is 18. Do a bit of more math. Well, that's going to be, let me make sure I'm doing all this correctly. I think I am. Yeah. Okay. Oh wait, no. Okay, wait, no, I did do a little hiccup there. It's asking for VA, not the current through not the current through that resistor. So VA actually is just going to be V1 minus 9. You see that? Because it's the voltage difference across V. And my bad. Okay, one more time. It asks for the voltage difference from left to right. So actually, it's going to be 9 minus V1. That's the final answer. Believe me this time, because it's asking for the voltage difference between the right and the left. It's saying the right is between the left and the right. The left is positive, the right is negative. So that's going to be 9 minus V1. So now instead of this, you get minus 2 times 9 minus V1. Then you do some more math. You get minus 2 times 9 is 18 plus 2V1 equals 18. 9V1 equals 36. And then I wrote 38, that's a 6. And then V1 will just equal 4. And that's your V1. And then it's asking for the power associated with the dependent voltage source. So the dependent voltage source, we can find the voltage now, right? Because we can say VA over 2. That just equals, well, VA is 9 minus V1 over 2, right? And then that's going to be 9 minus 4 over 2, which is just 5 over 2, or 2.5 volts. And then for power, we also need to get the current. So the current through that is going to be whatever the current through this 10 ohm resistor is, right? Because there's only one path. The current through the 10 ohm resistor has to be the same as the current through the source. So I'll just call this I for now, just to write an equation. So we have I equals V1 minus VA over 2 over 10, which is actually exactly what we saw earlier. So we actually have all these values now, though. It's 4 minus 2.5 over 10, which is then 1.5 over 10. Let me make sure I'm doing this all right. Yeah, exactly. And then that is going to be 0.15 amps. So now, remember, we assumed that I was going down, and we got a positive number, which tells us that we guessed right, and it is actually going down. And then the polarity of this voltage source has the plus on top and the minus on the bottom. So that means that we have a voltage drop in the same direction as the current, which means that our voltage here is positive. So that means the power of the source, I'll just draw a little symbol there, is equal to IV, which is equal to 0.15 times 2.5. Can draw some little arrows, which is finally gets us to, let me plug that into a calculator real quick. Okay, yeah, 0.375 watts. And that would be your final answer for that. So hopefully that gives a bit more. Actually, I still have like 15 minutes. Would you guys appreciate me going over the supernode question from the homework? Because that was just a pretty good question as an example for that. Or do you guys think you have that? I'll do it if you want.
Yeah, could you go over it, please?
Yeah, okay. So for this one, because it's actually in the textbook, I'll just draw it again. So got the 6-volt source. Got the okay. This one's actually pretty good because it involves a lot of the like small mistakes you can make with supernode. So here, I'll call the nodes by just V1, V2, V3. And I've put the 0 volt down at the bottom as normal. So as you can remember from before, supernode is found when you have two nodes separated only by a voltage source. So that would be your supernode here. Your supernode equation would be that V1, oh God, it would be that V1 plus 6 volts equals V2, or you could write it as V2 or V2 minus 6 volts equals V1. They're the same equation. I'll just leave it as that first one for now. And so for V1 here, I'll just, oh wait, no, yeah, the supernode. You have the supernode and you're writing the supernode equation. And you start by doing that with the stuff going in and out of V1. So the supernode, I think this might technically be called the supernode equation. And then this is like the supernode KVL. I don't know the proper terminology for it. Whatever Zorman says is right is right. It doesn't really matter. You don't have to label your equations that nicely on a quiz anyway. So again, I will assume all currents are going out unless specified otherwise. So here is a case where it has actually specified otherwise. So I'm going to say that this is going down, but we know that this is going in, right? because we have that 2 amp source here that goes like that. So, and similarly, I will assume that this is going out and this is going out. And now I'll write the supernode KVL, or not KVL, KCL. KCL. There you go. Okay. So the supernode, do you have a question? I hear someone talking. Or is you just not muted? I'll keep going. So V1 minus 0. I'm starting with this one going down here. V1 minus 0 over 0.5 ohms. And then just like we do with the normal node voltage equation, you just sum all the currents and say it equal to 0. So you have V1 minus 0 over 0.5. And then now we have minus 2 amps because there's that 2 going directly into the supernode. And then for the V2 ones, we have V2 minus 0 over 0.5 and V2 minus V3 over 0.5, and that equals 0. And then we only actually have to write one more equation because of that V3. So for V3, we have V3 minus V2 over 0.5 equals 0. Nope, why not just autopilot there? V3 minus V2 over 0.5, and then minus because it's going in here. Oh, could you clarify why? Okay, so, oh yeah, and it says IX here. Can you clarify why on V1 the current below is downwards and the given current for IX from V2 is downwards? Following that. So yes, that could be the case, but you really don't know. So the question for people listening is, could you clarify why on V1 the current is downwards when the given current for IX from V2 is downwards? So following that, the current would be clockwise up or up towards V1. So that could be the case. So what you're saying is that it would be going like that. However, it's just as possible that it could be going like that, and this current could also be going down and merging with it. And they both go up through that 4 amp. The key thing here is that you don't know. And since you're doing math, you can just say things are variables, and if you guess wrong, then you'll get a negative number, which is fine. And then you know that your guess was just in the wrong direction, but you still got the right number. So that's why you can assume that. And so yeah, that IX, that was actually like defined for us, because that's the thing we're actually solving for in the end. But anyway, going back to V3, we have V3, the 4 amp is going in, so minus 4 amps, and then plus 2 amps going out equals 0. And then you can solve this really however you want. The goal here, of course, is going to be to find IX. And IX is going to be V2 minus 0 over 0.5. That's just what path that is, or just 2V2. And you have enough equations to solve for that. Just a real straightforward way to do that is with this one, it's actually pretty nice. These two sum, and then you can just say that V3 minus V2 over 0.5 equals 2 amps. So that's telling you that in this direction here, we have 2 amps, which makes perfect sense because you have 4 amps going in and then 2 amps going up. So then you have 2 amps going to the left in order for it to sum to 4 amps again. So once you have that, this is equal to the negative version of it's basically equal to that one in the other equation. So then just going back from the other equation, I probably should have done this in a bit of a different order, but to simplify the other equation, right, you have 2V2, that's just dividing by 0.5, minus 2, I wrote V2, I should have said V1, sorry. 2V1 minus 2 plus 2V2, and then we just said that V3 minus V2 over 0.5 is 2 amps, so that would say that V2 minus V3 over 0.5 is going to be minus 2 amps. And that equals 0. And then from there, what do we do here? Just fumbling a bit. Yeah, And then, so that says that 2v1 plus 2v2 equals 4 amps, right? And then v1 plus v2 equals 4. And then plugging in this equation from up here. Sorry, my voice is dying a bit. I should have got some more water. So v2 equals v1 plus 6. So we can say v1 plus 6 equals 4. That tells us that 2v2 equals -2. So v2, no, v1 equals -2, sorry. v1 equals -2, so then v1 equals -1. Therefore, v2 equals -1 plus 6, so which is 5. And then, did I do this wrong? I hope I didn't. I might have done this wrong. What is the answer this supposed to be? I might have made an algebra error somewhere along the way. Forgive me if I have. Oh, yeah. Silly. Wait. Does anyone see the algebra error I make? The final answer, this is supposed to be a 4, and then you get 8 as the final answer. But
Yeah, it's v1 plus v2. I think you're at 4 instead of 2.
yes, thank you for catching that for me. Happens to the best of us. And then this. Okay. Yeah, so then this is 2 amps. This is still 2 amps. And then we subtract over the 6, we get, yep, -2. And then v2 equals -2 plus 6. This equals 4. And then we plug this into this. Ix equals 2v times v2 equals 8 amps. This is kind of weird because I'd simplified it to 2v2, but the unit's still amps because it's asking for a current. And yeah, does anyone have any questions or anything else they want me to go over? Okay, if not, then I will end it here. And, oh, okay, well, I'll answer these other questions in the chat. Is the quiz going to focus solely on node voltage, supernodes, and mesh? I honestly don't know. Sorman does not share the quizzes with TAs beforehand, so I'm going just based on, I looked at the class notes for this past week, and I saw he went over node voltage, mesh current, and supernode. So I'm assuming that's all that's going to be on the quiz. Of course, you still need to know what you learned in the past weeks, but in this class, largely everything you learn just builds as you go, and you have to keep using it anyway. So basically, with the Zorman, you can really expect, like, if you learn something on Wednesday, it's probably fair game for the quiz. That might change as the semester goes on, just because there's, like, he goes faster in class than there is time for them to give quizzes. So, like, I remember when I took this class with him, sometimes, like, the quiz would be on something we learned the previous week, and it's kind of rough because you might have forgotten it by then. But I'll make sure that I know kind of what's going on. Can you get the answer key for quiz 1? Is that not posted? It might be just posted in files. Yeah, if you go to, this is same with the homeworks. If you go to the Canvas page under the files tab, he has both the homework solutions and the quiz solutions. They're just there for you to read with Zorman's beautifully detailed work on them. Yeah. Any other questions? Okay, if not, then I will end it here. Good luck on your quiz tomorrow. Yep. Bye-bye.